that I don't forget. So please note that this is not an exponent, that is an inverse trigonometric functions. So please, let's say we take an example. Let's say we had, um, let me have a ratio. Let's have a ratio of sine theta. It's equals to sine theta, we said is y over r, isn't it? So let's say we want to find a solution of theta. So if we want to find solution of theta, we know that we are going to apply arcsine on both sides. We apply what we call arcsine on both sides of the function. So sine of theta equals to, even on the right hand side, we apply arcsine. Now in the ratio y over r. So therefore, now arcsine with a sine of theta, it cancels out, we get theta. And therefore theta is equals to arcsine y over r. So that's why when you're solving for solutions, we're utilizing that and say, oh, you're not transposing, you're applying arcsine on both sides of the function. Say in n format. So that's how we get theta. So please try it using, let's say just punch in your calculator arcsine of sine 30 degrees. I hope you see you'll get 30 degrees. So shift sine 30. So swap, you'll see you'll get 30 degrees. Yeah. So that's how it is. So when you apply arcsine, that's what we get. So I hope that is clear. So when you see the inverse trigonometric functions, or let's say negative on sine there, it's an inverse function. So if let's say you have, let's say when you talk about graph of sine, if let's say graph of sine theta, let's say maybe given that from 0 degrees, what we call the domain to 2 pi, which is 360. So if we have the graph goes there, amplitude, then it reaches 2 pi. Then here it's pi. Here it is pi over 2. Here we're going to have, I think it's 3 over 2 pi, 3 over 4 pi. Yeah, I think it's 3 over 4 pi in that point. So let's say the graph, this is graph of sine theta. So the inverse of let's say arcsine theta given to the same domain. The graph, it's an inverse. What it does, it's going to do the amplitude in this way, vertically up. Given the domain, it is the range now. Let's say range. Let's say the range is from 0 to 2 pi. Or let's say, yeah, we can give the range of, let's say, the graph from 0 to 2 pi. So this is the inverse of sine. So it opposes the, not really opposing. If let's say the axis you're using to plot the sine graph, the other one you plot vertically up. So that is the inverse of theta, of sine. Okay, I hope that is clear. So at least you have a better glimpse of inverse trigonometric functions. Even when it comes to cots and then sec, we have the inverse graphs. Okay, so I just want to take one example when we derivate, or maybe let me start writing the formulas here. The rows. So if we have to derivate, for an example, arcsine, let me put f of x. We can use x or f of x. But dy over the x for that function, y prime. So y prime it is equals to. So the rule says that you're going to have this in the denominator, you're going to have 1 minus the function inside the sine all squared. So you'll have the function inside sine all squared, f of x all squared, inside the root. Therefore, in the numerator, you must multiply by the derivative of the function. So you must have f prime of x. And this is given in the formula sheet, but you must know how to prove these formulas. So we're going there. So, but in another case, if let's say we assume this was x, then the derivative of x in the numerator is 1, and we'll have root 1 minus x squared, f of x all squared. Let me write it as x here, arc sine x. So if we assume if it was x, therefore the derivative there, it will be 1 over root 1 minus x squared. So just check the derivative of x, it's 1, that's why f of x, it is f prime of x in the numerator. So we use f of x in placement of functions, because we can have sine x there. Not even sine x, I want to say ln x, or let's say x squared, for an example. Okay, so let's look into, if let's say we want to derivate cos, arc cos, not cos. Arc cos, let's say f of x. So the derivative of arc cos f of x will be equals to. So it's similarly to the arc sine. Same thing, we are going to, in the square root, we'll have 1 minus the function which was inside the arc cos. It must be all squared underneath the root. In the numerator, we're going to multiply by the negative derivative of f of x. So we're going to have negative f prime of x. Negative f prime of x. So same thing, please note that it can be x. So if it's x, derivative of x is 1, then all divided by 1 minus x squared. Because f of x, certainly if we assume we are having arc cos x for basic rule. So y prime will be equals to negative 1 over root 1 minus x squared. So if let's say we have y equals to arctan f of x, so arctan f of x, the y prime of dy over dx is equals to. So the rule is that we are going to have 1 plus f of x all squared. So this one is not underneath the square root, so it's f of x all squared. Then in the numerator multiply by the derivative of f of x, which is f prime of x. Or we'll have 1 over 1 plus x squared. That is tan derivative of arctan. That is the derivative of arctan. So while we are still playing around, so we'll have, let's say, arc cosec. If we have arc cosec f of x, so arc cosec f of x, the derivative is equals to. In the numerator, we're going to have negative the derivative of the function and all divided by. We're going to have f of x multiplying the root of f of x all squared minus 1. That is the derivative of, it's not clear there, but negative f of x all in all multiplied by the denominator f of x root f of x all squared minus 1. Minus 1. Let's just add it here. So similarly with the arc sec f of x. So the derivative of arc f of x It's going to be equals to, so this one we have the derivative of the function inside the arcsec. They're all divided by f of x. Inside the root, we're going to square the f of x added by minus 1, or we subtract 1. So the tricky part is when you see arc cos and arc sine, they have the same, the only thing is the negative output of the differentiation. Same thing with cosec and sec. The difference is the output of the negative the negative there of the let's say the fraction or the differential. So I just want to pass by proving either two of them. So if let's say the question you are having given a question that we need to prove the derivative, prove dy over dx for what now? For y is equals to, let me use arcsec x. So if we need to prove the following, so there's few things we need to recall. We need to recall square identities, and we need to recall the method of now getting rid of the arcsine. So what we're going to do, we can say let, or you can say you apply arcsine on both sides, or you can say that I'm going to apply sine on both sides. I want to make x subject of the formula. You need to make x subject of the formula. So we're going to have sine y is equals to x. When you apply sine on both sides, if you remember, we apply sine, get rid of the arcsine. We apply sine on the other side, we'll have sine y. So x now we know is equals to sine y. Now we need to differentiate implicitly, so in terms of x, because now y is in terms of the function y, or let's say y is in the midst of sine, or the trigonometric functions. So what we're going to do, we're going to differentiate sine, where we're going to have cos y, isn't it? And therefore, make sure you multiply by a change in y over change in x, because derivative of sine y is sine y. Therefore, derivate the angle there, which is dy over dx. I hope you agree. Therefore, it's equals to derivative of x in terms of x. That is equals to 1. When we're done, we need to make dy over dx subject of the formula. So dy over dx subject of the formula, divide on both sides of the function by cos y. So we'll have 1 over cos y. But we're not done the function. It's in terms of what our derivative, I want to say, is in terms of y. So we must make sure that we express it in terms of x. We know that x is equals to sine y. We need to try and replace cos y and express it in terms of x. How will we do that? So that's where now we recall the square identities. We know that cos squared, let me use y is equals to 1 minus sine squared of the same angle, sine squared y. So what if we try and apply a square root on both sides? When you apply a square root on both sides, you get rid of the square. Therefore, cos y is equals to root 1 minus sine squared y. So sine squared y. And please, when you apply a root in a high level maths, we're not expecting that you'll apply in individual terms. That's math error. Applying at once in both terms, then they are being locked by the root. So therefore, now we can replace cos y. We know it is in terms of sine. The answer will be equals to, we'll have 1 over. So we said cos y, it is 1 minus sine squared y. We are not done. At least y, we're trying to replace cos y because we know we're given sine. So we're given that. So we know that we can take it and substitute there. We can substitute there. So sine y, we know it equals to x, isn't it? So 1 over root 1 minus. So sine y we said is x, therefore sine which was squared. So it's 1 over root 1 minus x squared. So that's how you prove the derivative of arc sine x. Derivative of arc sine x. So I hope you see we said the derivative of arc sine x is 1 over root 1 minus x squared. So that's what we're trying to prove. We need to recall square identities. And mind you, when it comes to tests and exams, you'll have to know how to prove the derivative of the functions. Even cosine, we know how to prove it, isn't it? From first principles. So proving the arc sines, we prove using our even square identities and implicit differentiation. Okay, just want to close the one last one. The other one you prove at home. So let's say if we are given, let's say we want to prove the derivative of, let's start with cosec. Arc cosec, not cosec. Prove the derivative of arc cosec. So the derivative of arc cosec, we know that at the end we must have negative 1 over f of x times the square root of x squared minus 1. But you must make sure the steps must correlate, it must communicate. They must correlate. Okay. So what we're going to do, we want to get rid of arc sine, that's the first step. Therefore, we apply cosec on the other side of the equation. When we get rid of that, we're left with x. Now, the second part, we need to differentiate implicitly. So, what is the derivative of cosec y? Derivative of cosec y is negative. It's negative cosec. Cosec y times cot y. Therefore, let's not forget the derivative of y, the angle, dy over dx equals to derivative of x in terms of x, it is equals to y. From there, we need to make dy over dx subject of the formula. Divide on both sides by negative cosec y cot y. Now, the third thing that you need to recall again is the square identities. So you can do it on the side, your square identities. You'll have to put it here. So I say recall. So if we recall square identities, we stick into the cosec. So at least cot y to say. At least we see that we're given cosec y, we can replace it by x. But what about cot y? So we need to check that cot, let's use y. So let me just put square. Cot squared is equals to what? It's equals to cosec squared y minus y. That is the square identity, because 1 plus cot squared is equals to cosec squared y. So it's there in your formula sheet. 1 plus cot squared is equals to cosec squared y. So we took y to the other side. We're making cot y subject of the formula. So after making cot squared subject of the formula, we know that putting the square root on both sides, we get rid of the square. So we have square root of cosec squared y minus y. Therefore, we can replace the values of cos y and cosec y and cot y. So therefore, it will be equals to, in our main derivative, it's equals to, let's say, -1 all divided by. So cosec y we said is equals to x. And in the meantime, let me start by replacing first. So we know that cot y is cosec squared y minus 1. So we're not done. It is still in the implicit form, having x and y. We're replacing everything. We'll have square root. So cosec squared or cosec y, we said cosec y is equals to x. So it is squared, it will be x squared, therefore minus 1. We replace cosec by x, which is x. Then it was squared, even the x is squared. So that is the derivative of arc cosec x.